Okay. This is a steam turbine example problem illustrating the use of control volume analysis for the first law of thermodynamics. We have one inlet, one outlet. We have a shaft that is transmitting work from the turbine outward. We have a control volume, and we have these inlet conditions: inlet pressure, quality, mass flow rate, exit pressure, exit quality. Velocity is not given. That's a clue that velocity will not be included in the final calculation, most likely. In real-world applications, we should not ignore it. Going deeper into the analysis and solution. First, we identify the process. In this case, we call it adiabatic expansion of steam, converting thermal energy to mechanical energy or work. In turbines like this, we assume that the heat transfer is negligible. We also assume that we're dealing with pure steam, so we can use steam properties. Finally, we're going to calculate the work output of this steam turbine. Pause and reflect on how we might attack this one. What's in our toolbox? What conservation laws can be used? How will we get the properties once we've pruned down those conservation laws? That's the mindset you want to have. So let's assume that it is steady state, that we'll apply the first law, that we're looking at the control volume. Heat transfer is 0, and there's one flow in and one flow out. We certainly have continuity, saying that mass flow in equals mass flow out. Straightforward. The conservation of energy is a little bit more complicated. We have a heat transfer term, we have mass in terms, mass exit terms, and work terms. To simplify, you can see I've crossed out heat transfer because we do assume it's adiabatic. I've crossed out the masses because I've assumed the same mass flow in as going out, so it's called one flow in, one flow out. I've crossed out the GZ terms because no elevation values were given to me. I've left the V's to make one more statement about them. Usually VI squared divided by 2 and VE squared divided by 2, which without dividing through by 1,000 would give you joules per kilogram, are much, much less than the enthalpies. In fact, the rule of thumb is that if the delta of velocity or the delta of elevation are not in this range, you can largely neglect it. As you can see, these values result in about 1 kilojoule per kilogram worth of energy. As a result, the final and most important reduced equation is the specific work equation. Now the challenge, in order to finish up the solution, is to find the values of H's. HO is essentially H sub F plus X, the quality, times H sub Fg, all evaluated at saturation values of 0.15 megapascal. The HI is even simpler because it said it came in at saturated conditions. Therefore, you can look it up directly and gather this number, 2802 kilojoules per kilogram. Pulling this all together, we calculate a delta H of 153.2 kilojoules per kilogram. Multiplying it by the mass flow rate will give you the total power output from the steam turbine of 11 megawatts. How does that compare to other quantities? Well, rolling power on an average day has to generate 6 to 8 megawatts. Salem, though, is far greater at 2 gigawatts. In review, making sure that visual clarity is established. One in, one out. That's not always the case. Recognize that we're producing mechanical work. Recognizing the inlet and exit conditions. Being very explicit about the process, explicit about the property lookups, and what we're looking for. Recognizing that steady state is assumed, one flow in, one flow out, using conservation of mass, conservation of energy, pruning them down with given assumptions. We get to the final, most important equation. We then return to our property skills, looking those up, and finally finishing with the final calculation. Right here. I hope this has been useful, and if there are questions, let's discuss them in class. Thank you.